Bismillah ar-Rahman ar-Rahim. In this video, we have two logarithmic integrals. Let's start with this one, the integral from 0 to pi over 2 log 1 plus 4 sine x to the power 4. The first step is a change of variables. Y is equal to 10x when x is 0, y is 0. When x tends to pi over 2, y tends to infinity. dy is sec squared dx. Sec squared is 1 plus 10x squared, which is 1 plus y squared. So dx is dy over 1 plus y squared. Sine x is 10x over sec x. If we raise sine to the power 4, we get 10x to the power 4 divided by sec x to the power 4, which is sec x squared, and this sec squared is 1 plus 10x squared. This is 1 plus y squared. In the numerator, we have y to the power 4. Our integral becomes from 0 to infinity dy over 1 plus y squared, the natural logarithm of 1 plus 4y to the 4 over the square of 1 plus y squared. The argument of the logarithm is 1 plus y squared all squared in the denominator. In the numerator, we have 4y to the power 4 plus 1 plus y squared all squared. We can think of the numerator as 1 plus y squared all squared minus 4y to the power 4. This is I times 2y squared all squared. We have a difference between two squares. The numerator can be written as 1 plus y squared plus 2i y squared. The other bracket is 1 plus y squared minus 2i y squared. This is equal to 1 plus 2i times y squared. The other bracket is 1 plus 1 minus 2i y squared. This is the complex conjugate of that. The integrand contains the logarithm of 1 plus 2i times y squared plus log 1 plus 1 minus 2i times y squared, then minus 2 log 1 plus y squared. Every one of these terms is divided by 1 plus y squared. We have three integrals. The second one here is the complex conjugate of the first. So we can focus on the first one, then take the real part and multiply by 2. We can take 1 plus 2i as a common factor. Then we get y squared plus 1 over 1 plus 2i. If we multiply the numerator and the denominator by 1 minus 2i, we get 1 squared plus 2 squared in the denominator, which is 5. We need to deal with these two integrals. Let's do this one first. Integral from 0 to infinity log 1 plus y squared over 1 plus y squared. Do the change of variables. Y equal to tan theta. When y is 0, theta is 0. When y tends to infinity, theta tends to pi over 2. dy is sec squared theta d theta. That's 1 plus y squared d theta. So d theta is dy over 1 plus y squared. This part here becomes d theta, and we have the logarithm of sec squared theta, which is cosine theta to the power minus 2. We can take this minus 2 outside. We have the integral from 0 to pi over 2 log cosine theta d theta. If this integral is alpha, alpha is also the integral of log sine theta, theta from 0 to pi over 2. We can obtain this integral from that one by changing theta to pi over 2 minus theta. Consider the integral from 0 to pi over 2 log sine 2 theta. Sine 2 theta is 2 sine theta cosine theta. This integral here can be written as the sum of three integrals from 0 to pi over 2 log 2 d theta plus the integral from 0 to pi over 2 log sine theta d theta. This is alpha. The third integral is from 0 to pi over 2 log cosine theta. This is also alpha. This integral is equal to 2 alpha plus from here we get pi over 2 times log 2. We can do this integration in another way. The argument of the logarithm is sine 2 theta, which looks like this on the interval from 0 to pi over 2. We have symmetry about pi over 4. This integral is twice the integral of sine 2 theta from 0 to pi over 4. Let's do the substitution. Theta bar is equal to 2 theta. 2 d theta is d theta bar. Log sine 2 theta is log sine theta bar. When theta is 0, theta bar is 0. When theta is pi over 4, theta bar is pi over 2. We get this integral here, which is exactly equal to alpha. Thus, 2 alpha plus pi over 2 log 2 is equal to alpha. Moving alpha to the right-hand side, pi log 2 over 2 to the left-hand side, we get that alpha is minus pi over 2 log 2. This integral here is minus 2 times alpha, and then there is another minus 2 here. Our integral of interest has a term equal to 4 alpha, that is minus 2 pi log 2. We also have 2 times the real part of the integral from 0 to infinity, log 1 plus 2i y squared plus c, which is 1 minus 2i divided by 5. Downstairs, we have 1 plus y squared. We can split this logarithm into log 1 plus 2i plus log y squared plus c. Integral from 0 to infinity of 1 over y squared. This is tan inverse y. When we use the limits of integration, we get pi over 2 minus 0. That's pi over 2. So this part becomes double the real part of log the complex number 1 plus 2i. In polar form, this is square root 5 e to the I 10 inverse 2 times pi over 2. This is the logarithm of square root 5 plus I 10 inverse 2. Because we are taking the real part, this goes away, and we are left with pi times the logarithm of square root 5. We need now to obtain this integral here. Let's define I of t as integral of the logarithm of t times y squared plus c divided by y squared plus 1. Our integral of interest is I of 1. If t is equal to 0, we have log c in the numerator, that's a constant, and the integral is log c times pi over 2. Let's do differentiation under the integral sign. The first derivative of I with respect to t is the integral from 0 to infinity, 1 over y squared plus 1. If we differentiate this logarithm with respect to t, we get downstairs t y squared plus c and y squared in the numerator. Let's do partial fractions. The integrand here can be written as 1 over t minus c times 1 over y squared plus 1 minus c over t minus c 1 over t y squared plus c. This is equal to t minus c y squared plus 1 t y squared plus c. In the numerator, we get t y squared plus c minus c times y squared plus 1. That's minus c y squared minus c. So we get t minus c times y squared. This is exactly what we have here. We can split this into two integrals. In the first one, we get pi over 2 times 1 over t minus c. In this part here, take t as a common factor. So we have 1 over t minus c over t, 1 over y squared plus c over t. When we integrate, we get 1 over t minus c over t, 1 over the square root of c over t, tan inverse y over the square root of c over t. When we use the limits of integration, this becomes pi over 2. So we end up with pi over 2 times 1 over t minus c. Then we have the square root of c over t. This is what we currently have. Integrate both sides with respect to t from 0 to 1. So from here we get I of 1 minus I of 0. And I of 0 is pi over 2 log c. We get these two integrals, which when added to pi over 2 log c, give us I of 1. The integral from 0 to infinity log y squared plus c over y squared plus 1. This integral is log t minus c. When we use the limits of integration, we get log 1 minus c minus log minus c. Recall that c is the complex number 1 minus 2i divided by 5. Every logarithm here is meant to be the principal branch. Let's do the indefinite integral dz 1 over the square root of z minus c. Let z be equal to minus c w squared. Z minus c becomes minus c w squared minus c, which is equal to minus c between brackets w squared plus 1. dz is minus c 2w dw. Z to the 1 half is minus c to the 1 half times w. This w and that w go away. Also, this minus c and that minus c. We are left with 2 over the square root of minus c. Then the integral of 1 over w squared plus 1, which is the inverse tangent of w. Write down w in terms of z. So we have the inverse tangent of z to the 1 half divided by minus c to the 1 half. Let's write the inverse tangent or arctangent function in terms of logarithms. Tan inverse gamma is 1 over 2i log 1 plus I gamma over 1 minus I gamma. So this inverse tangent is 1 over 2i log 1 plus I, the square root of z, over the square root of minus c. Downstairs, we have the same quantity but with a minus sign. To get our integral, we multiply by this factor, which is 2 over the square root of minus c. Our integral is equal to minus I divided by the square root of minus c. Then this logarithm here. The argument of the logarithm is a ratio. Multiply the numerator and denominator by the square root of minus c. We get minus I over the square root of minus c log minus c to the 1 half plus I, the square root of z. Same thing downstairs, but this plus sign becomes a minus sign. This is the indefinite integral. We have a definite integral from 0 to 1. If z is equal to 0, we get this times log 1, which is 0. Now, if z is 1, then we get this quantity here. The square root of minus c is written as I times the square root of c. This integral is equal to pi over 2 log c. Then we have these two logarithms. The first one I write as log of minus between brackets c minus 1. So this is log minus 1 plus log c minus 1. And then we have this logarithm. I can also write it as minus log minus 1, which goes away with this term, minus log c. This minus log c, after being multiplied by pi over 2, cancels this term. The surviving terms are log c minus 1 times pi over 2 plus this term here. Write down c minus 1 as c to the half plus 1 times c to the half minus 1. When we combine these two logarithms, we get pi over 2 log the square of the square root of c plus 1. The integral of interest is equal to minus 2 pi log 2 plus pi log the square root of 5 plus 2 times the real part of this quantity. This is pi times the real part of the log of the square of c to the half plus 1. Log a complex number z is log the magnitude of z, e to the I, the angle of z, say theta. So this is the logarithm of the magnitude plus I theta. Since we are interested in the real part, we only care about the logarithm of the magnitude. So our result is pi times the logarithm of 1/4 plus pi times the logarithm of the square root of 5. Then we have pi times the logarithm of the magnitude squared of this complex number. C is 1 minus 2i over 5. In polar form, this is 1 over the square root of 5. E to the power I times the tan inverse of minus 2 over 1. The principal square root is 1 over 5 to the power 1 over 4. E to the minus I over 2 tan inverse 2. We add 1 and then take the magnitude squared. We have a bracket 1 plus 1 over 5 to the power 1 over 4. E to the minus I over 2 tan inverse 2 times the complex conjugate 1 plus 1 over 5 to the power 1 over 4. E to the I over 2 tan inverse 2. When we multiply to get the magnitude squared, 1 times 1 is 1. This times that is 1 over the square root of 5 because the exponentials multiply to unity. Then we have two terms, 1 over 5 to the power 1 over 4. We have the sum of the two exponentials. This is 2 cosine tan inverse 2 divided by 2. Write down this factor as the product of 1/2 times the square root of 5 over 2. Take this inside the bracket. So we have the square root of 5 divided by 2. When this is multiplied by 1 over the square root of 5, we get 1/2. Note that these two guys together are 1 plus square root 5 over 2, which is the golden ratio. Then this 2 goes away with that 2, and we end up with 5 to the power 1 over 4 times cosine tan inverse 2 divided by 2. 5 to the power 1 over 4 is 5 to the power 1 over 2, all to the power 1 over 2. Cosine tan inverse 2 over 2 is the square root of 1 plus cosine tan inverse 2, all divided by 2. This is equal to the square root of the square root of 5 plus the square root of 5 times cosine tan inverse 2, all divided by 2. The acute angle, whose tangent is 2, has a cosine that is equal to 1 over the square root of 5, which means that this cosine here is 1 over square root 5, and this term is equal to 1. So under the square root, we also have the square root of 5 plus 1 over 2. That's phi, the golden ratio, to the power 1 over 2. Our integral is equal to pi times the logarithm of 1/2 phi, the golden ratio, plus the square root of the golden ratio. Our other integral is x from 0 to 1 log 1 minus x plus x squared over x minus x squared. Let's do partial fractions. Write down 1 over x minus x squared as 1 over x plus 1 over 1 minus x. Split the integral into two integrals. Take this integral here. It's written using the dummy variable of integration y. Do the change of variables, y equal to 1 minus x. dy is equal to minus dx. When x is 0, y is 1. When y is 1, x is equal to 0. But we can use this minus sign to have our integration from 0 to 1. We have x downstairs. The argument of the logarithm becomes 1 minus x plus 1 minus x whole squared. If we expand and simplify, we obtain the argument of the logarithm as 1 minus x plus x squared. So this integral is exactly equal to that integral. The integral of interest is double this integral here. X cubed plus 1 is equal to x plus 1 times x squared minus x plus 1. We can use this to write down the argument of the logarithm as 1 plus x cubed divided by 1 plus x. Write down this logarithm as log 1 plus x cubed minus log 1 plus x. So we have two integrals. Let's focus on the first. Here written using y. Do the change of variables. Y cubed is equal to x. That is, y is x to the power 1 over 3. dy is 1 over 3, x to the minus 2 over 3 dx. We have log 1 plus x in the numerator. In the denominator, we have x to the power 1 over 3. These two terms together, they give us x in the denominator. So this integral here is exactly this one multiplied by 1/3. This means that our integral of interest is minus 4 over 3 multiplied by this integral here. Let's do integration by parts. The product of the logarithms when x is 1 is log 1 times log 2, that's 0. When x tends to 0 from above, log x tends to minus infinity, log 1 plus x tends to 0. We can use L'Hopital's rule to obtain that this limit is equal to 0. This integral is minus the integral from 0 to 1 log x. Then we have the derivative of log 1 plus x, which gives us 1 plus x in the denominator. 1 over 1 plus x is summation j from 0 to infinity minus 1 to the power j, x to the power j. We can do the integration term by term. To evaluate this integral, use the substitution x equal to e to the minus t over j plus 1. X to the power j is e to the minus jt over j plus 1. Dx is equal to minus 1 over j plus 1 times e to the minus t over j plus 1 dt. These two exponentials, when multiplied, they give us e to the minus t. What about log x? Log x is minus t over j plus 1. Minus 1 times minus 1, that's 1. When x tends to 0, t tends to infinity. When x tends to 1, t tends to 0. We can use this minus sign here to get our integration limits from 0 to infinity. The integrand is t e to the minus t. We also have 1 over j plus 1 squared. The integral is equal to 1. And so we get this as our result. This is the Dirichlet function, eta of 2. We know that eta of s is equal to 1 minus 2 to the power 1 minus s, zeta of s. S in our case is equal to 2. So this bracket is equal to 1 minus 1 half. That's 1 half. We have zeta of 2, which is pi squared over 6. So this integral is pi squared over 12. If we multiply this result by minus 4 over 3, we get that our integral of interest is equal to minus pi squared divided by 9.